Okay, let's talk some more about free body diagrams. To the right is a complete free body diagram. It contains all the forces that act on the object. Every force is identified with a label and a direction. We tell the directions with the direction of the arrow. It doesn't have too much detail. A rough sketch is all you need. Remember, you're really diagramming the forces, not making an artistic drawing. On a free body diagram, include every force that acts on the object, weight, normal forces, and applied forces from springs, ropes, and other sources. The isolated object acts exactly as it did before, being removed from contact with the environment. In other words, what we've done is we've isolated, in this case it's a dumbbell, but we've isolated it from its environment, and every contact it has with its environment, whether it's the field force of the weight or this mysterious applied force. Oops, the bird is trying to get in on the act. Or whether it's the contact force of the normal forces on whatever surface this is sitting. These forces are how the dumbbell is actually connected to its environment. So you're isolating it from its environment and just listing the forces that really connect it to its environment. And once you have all the forces on the diagram listed, you can actually say a little something about how this thing is going to move or not move, for that matter. Every contact with a surface creates a normal force. Normal forces may be vertical, horizontal, or at any angle. Notice how these normal forces are always perpendicular to the surfaces that applied them at the point of contact. So, if we were to draw a force in here, right, it would go something like this. The force here at the point of contact would be along this axis, right? So this is the one from the incline. This is the one from the wall. Okay, so it's perpendicular to the surface at the point of contact with the object. Styles of free body diagrams. There are two different styles you may see for drawing free body diagrams. A block of mass M sits on a floor partially suspended by two springs. With the outline method, you have the outline of an object. Forces may point to or from the object. Forces drawn about where they act. A point mass method, object represented as a point. All forces point away from the object. Both of these are correct. Some of them have advantages and some have disadvantages depending what you're doing. Let's get into that a little bit. The outline method. Free body diagrams used in engineering, such as for building codes, were done with the outline method because the positions of the forces matter. You may want to know a little something about what the position of the forces are. Also, if you shrink this down to a point, sometimes you might have vectors that act almost along the same line, and it might be hard to see these if you were to draw it as it is when you shrink the object down to just a little point. Okay, so sometimes doing it this way makes the forces easier to see, and other times it's not as important. So force is a vector. To solve force problems, you have to choose which direction will be positive and which will be negative. I always say just pretend this is a number line, and the object itself is at the origin. If you go to the right, it's positive. If you go to the left, it's going to be negative. If you go up, again, positive. If you go down, it's going to be negative. So we say this is a sign convention, which means conventionally most people do it like this, but there are problems where it might be an advantage to say that down is positive and up is negative. If that should happen, I don't anticipate that'll happen during this year, but if that should happen and you reverse the sign convention, it's perfectly fine. It's just that when you get a positive result, know that that means down. And please, if you reverse the sign convention, don't accidentally revert back to the more conventional way of up being positive and down being negative halfway through the problem. You'll get the wrong answer. Okay, to solve force problems, you have to choose which directions will be positive, which will be negative. This choice is arbitrary, so we call it a sign convention. It's not a law. You can reverse them. Sometimes some problems are better solved with reverse directions. But most people do it like this most of the time. Choose the positive direction that makes the problem easiest to solve. Always make a diagram to remind yourself which direction is positive. Good idea. Okay, back to the net force. Let me just see where we are here. Okay. In most situations, there are many forces acting at once. Objects respond to the net force. In physics, net means total, taking account all directions. So if I wanted to find the net force here, what I would do is I would add F, which goes up, plus the normal force, plus second normal force over on the other side, minus the weight because that goes down. So this sum would tell me what the net force is. In most situations, there are many forces acting at once. Objects respond to the net force. I said this before, but it's important to emphasize the force in the second law is the net force. The net force is the thing that makes the mass change its motion. So F net here is the force, applied force acting up, plus the two normal forces also acting up, minus the force of the weight, which acts down, so that has a negative sign. Equilibrium is a special case where we say the net force is zero. So if the net force is zero, what that means is that the total force applied is zero, and therefore it's not changing its motion. So if the net force is zero, well, the mass hasn't dropped to zero, but the acceleration certainly has. And what that tells us is that this mass is not changing its motion. It's not accelerating. Doesn't mean it's standing still. It could be moving at a constant velocity. Think of a velocity of zero as one of many possible constant velocities. So the dumbbell is at rest. If the dumbbell is at rest, the net force must be zero. You could say the same thing if it was moving at a constant velocity. The box is shown at rest, so net force is 0. What is the normal force in these examples? Well, in general, oops, where am I going? We have an applied force up, a weight acting down. So for the first example there, the net force is 0, and that's equal to F minus the weight plus the normal force. So if I were to take this and solve for the normal force, I would get and since I don't want the negative of the normal force, I want the normal force itself, the mg minus F, and this is 10 newtons minus 4 newtons, and this is 6 newtons. Okay, so in that first example, that is 6 newtons. Over here, in the second example, we have 0 is equal to minus F minus mg plus normal force. So solving, the normal force is equal to F plus mg. Normal force is equal to 4 newtons plus 10 newtons, and the whole thing is 14 newtons of normal force. So the fact that the net force we know is 0 gives us an ability to solve for a missing force. Over here equals, so the applied force is up, the weight is down, and actually the normal force is also down. So if we solve this, we get normal force is F minus mg. Normal force is 15 newtons minus 10 newtons equals 5 newtons. Okay, I hope that makes sense. And here you can see what we found in the previous example. Okay, in the first we found out the normal force was 6 newtons. In the second we found out it was 14 newtons, and in the third we found out it was 5 newtons. And it's actually 5 in the negative direction, right? Because the normal force here points down. The surface is above the object, so the surface is pushing it down. Okay, hope that helps. Okay, do the problems that follow this, and see you soon.